Okay, here we have a function, f of x equals 2 to the x plus 4, and we're going to go ahead and graph it, sketch it. It's an exponent, and the exponent itself is a variable, so it's a little bit different. And usually when I see something relatively direct like this, I like to just plot some points. So that's the first approach we will use. And basically to do so, we form a little chart. Here's the x values and the corresponding f of x values. And you can see here, if you plug in 0, f of 0 is 2 to the 0, which is 1, plus 4, which is 5. And 1, 2 to the first is 2, plus 4 is 6, etc. going that way. And we get 4, 2 to the fourth is 16, plus 4 is 20. And then the negatives, 2 to the negative first is 1/2. See, reciprocal, so it's 4.5. And then negative 2 would be 2 to the negative 2, which is 1/4. And then 1/8, etc., etc. So you can see how the pattern, it's approaching 4, going to the left. And then going to the right, it's going to start accelerating and going, approaching infinity, it looks like. So let's go ahead and sketch this, okay? We'll take a quick graph. Here's the y coordinate, or the f of x coordinate. And here's the x. Alrighty, so we have x, and let's call this f of x. Okay, and we'll start with 0, 5, that's the y-intercept. And then 1, 6, 2, 8, and then 4, 20, and it looks like it's going to head up that way as the values get higher. And then as the x's go negative, you see how it starts approaching 4. And this actually would be a horizontal asymptote because it will never reach 4, y equals 4. And that's our sketch. And one quick note before the next sketch, notice too how you have a horizontal asymptote. So the domain of this is going to be all real numbers. In other words, you could put any value of x in there, any real number. But the range is going to be only numbers above 4. This number, 2 to the x, will never get to 0. So it'll approach 4. So our range will be all values greater than 4. Okay, our second graph, we have a function f of x equals the value of x minus 5 squared divided by 3. And again, you could plot some points, although with the 3 here you might have a lot of fractions, so I would try to do something else. And I'd probably look at this from the standpoint of trying to find the parent function and then graphing it that way. And the parent function of this is a quadratic. It's x squared. So let's rewrite this, make it more apparent. This is f of x equals, I'm going to make this 1/3, bring that in front, times x minus 5 squared. So here we have the x squared, and notice there's no horizontal shift because there's no number outside of the actual function. We do have a kind of a contraction, not necessarily a stretch. Every output is going to be divided by 3, or times 1/3. And notice too that this x value is minus 5, so we're going to have a shift to the right, 5 units. Okay, so let's go ahead and start graphing this. Okay, and actually I'm going to quickly, on the left side here, okay, again, if this were the parent function x squared, it would look a little bit like this. This is x squared. And again, if we had a shift to the right 5 units, we would have something that looked something like this. So this would be 5, 0. Okay, and then notice too that it's 1/3 of that, which means every one of these outputs, instead of being here, would be 1/3 of that. So it would probably be a wider graph, something like that. Just to keep in mind. So let's actually graph this more accurately. Alrighty, so let's start with again, we have the horizontal shift to 5 units. So we're going to start with 5, 0. And actually, if you were plotting points, if you plug in 5, you get an output of 0. Okay, and again, it is a quadratic, so it's going to be a parabola. And again, it's going to, instead of going up one fact, it's going to be a factor of 1/3. So let's actually sketch a little bit. 1/3 is going to be wider. Okay, but let's plug in some points to make it even more accurate. Let's first figure out what is the y-intercept. So we plug in 0 into x. So let's find f of 0. F of 0 is going to be 0 minus 5 is negative 5 squared is 25. 25 thirds, which is 8 1/3. So 0, 25 thirds. And remember that a parabola is always symmetrical. So if we went 5 units to the left to get to the y-axis, let's go 5 units to the right to 10 and plug in 10. 10 minus 5 is 5. 5 squared is 25 thirds. So 25 thirds is here. So we're going to have 10 25 thirds. And that'll give us our two sides of the parabola. And notice how the axis of symmetry is x equals 5, which was the horizontal shift. And there's our sketch, our parabola. And again, you could plot some more points if you want to confirm it. But we have a y-intercept, the vertex, which is also the x-intercept. And then we have 2 points on either side of the axis of symmetry, which gives us a good dimension and form of our parabola. Now the third function we're going to graph or try to sketch is a logarithmic function. And again, log base 2 of x minus 1 plus 1. Okay, and a little tricky, a little more complex, especially if you're not as comfortable working with logs. Not the greatest thing. However, what you do notice is there is a shift up 1 that we've seen from other functions, and a shift to the right of 1. So the trick really is going to be figuring out what does a log base 2 of x look like. Okay, and again, I'm not terribly comfortable with logs all the time, and especially if I'm not with a calculator, and I don't want to plug in all these numbers. So what I generally will try to do is figure out what the inverse is and use that to determine what a log function will look like. So what is the inverse of log? Well, the inverse of log is basically an exponential function, which we just graphed in the other example. So let's take a look at this. So let's say we have y equals log base 2 of x. What is the inverse of this function? Well, we know 2 to the y would equal x, okay, using just simple log methods. And if we want to find the inverse of something, we simply flip-flop the x and the y values, the inputs and the outputs. So the inverse of this is basically going to be y equals 2 to the x, which of course we just graphed on the other page with some shifts involved. So let's take a look at this. Let's graph both 2 to the x and log base 2 to the x, and so we have something to work with. Okay, so here's our sketch. Okay, if you recall, 2 to the x is, again, 0, 1 is one of our points, and then 1, 2, and then 2, 4, and going up this way. And then, of course, the negatives become fractions and with an asymptote, horizontal asymptote of 0, so it's going to look something like this. Okay, so this is what y equals 2 to the x. So now the question is what does log base 2 of x equal? Well, it's going to be the inverse of this, which is basically meaning we're just going to flip-flop all these values. And if you recall from inverses, they will actually reflect over x equals y. So basically, if this is 0, 1, this is going to be 1, 0. Okay, and this was 1, 2, so we're going to have 2, 1, and continuing this way. So this is going to go like that. Okay, and then these values over here are going to basically go around, and again, the horizontal asymptote becomes actually a vertical asymptote in many ways for this. And this basically is going to be the log base 2 of x. Okay, once we got our parent function taken care of, log base 2 of x, let's go back to our original one. It's g of x equals log base 2 of x minus 1 plus 1. And I even lightly sketched our parent function of log base 2 of x. Okay, it just uses the reference points. And again, we want to shift it up 1 and to the right 1. Okay, so again, instead of having a vertical asymptote, or boundary, if you will, of x equals 0, which is the y-axis, from x. Because remember, a log cannot be 0 or less than 0. So to correspond with that, we now have a shift to the right of our boundary, our asymptote, to x equals 1. So I'm going to just put that in lightly. Okay. Okay, so that's our shift to the right. And of course, we're going to shift it up 1. So let's take this whole graph and let's sketch it. And it's going to go like this and up 1 like that. Okay, so that is what this function is. And let's confirm some of the values, by the way. Notice how I intersected them at 2, 1. If you plug in g of 2, you will get a value of 1. If you plugged in the log base 2 of 2, you would also get 1, coincidentally. So that leaves these points, common points. But anyway, I also have some points down here that I wrote. We have g of 1 is undefined for this function, so there's our asymptote. G of 2 is 1, and g of 3 is 2, which is about right here, okay, which corresponds to that. And you can go on and just confirm the values. But anyway, this is the graph that we got from taking the parent function and shifting it up 1 and to the right 1.